Okay, so ladies and gentlemen, again, for those who came in late, if you could go through that little ritual you had to undertake last time to get the AnyLogic license. Alan's back there to help if anyone needs it, and then if you were to fire up AnyLogic after completing that, that should put us in good stead for today's exercises. Okay, so the video I asked you to review, what did that video concern? What was it about? Anyone? Stocks and flows. What are stocks and flows? Well, they're the primary building blocks of this first type of modeling that we're going to be reviewing, system dynamics modeling. The basic pieces, ladies and gentlemen, out of which we build these models. So what's a stock? Yes. Okay, so stocks collectively, if we look across a model that we're building, or if we think about a system out there in the world, the stocks collectively sort of define the state of the system. They encode the current state of that system. They define the current situation. Good. A particular stock can be thought of as an accumulation. It accumulates things in it, kind of like a bathtub accumulates water. And into a stock and out of a stock, we have what? Flows coming. Stocks are kind of like the nouns. They're describing the current situation, and they are acted upon by these flows, which act as kind of the verbs of the system. So we might have a population, and into it come births, out of it come deaths, and the stock represents the current population size, or sometimes we just abbreviate it to say the population. Now, in the video, I mentioned a way to sort of help delineate stocks from flows. And I'll recount it here again. Basically, you could imagine freezing time. The things that you could measure if you froze time, the number of people in the population, that would be a stock. The things that are changes over time, rates of change over time, the number of deaths per year, number of births per year, you can't measure them at any one point. In fact, things like that we often measure by accumulating. So we accumulate over a week how many people have died and use that to derive a sort of rate of a mortality rate for our city. And then we might rescale that from mortality rate per week over the week in which we measured it to a mortality rate per year by multiplying it times 52 weeks or what have you. But fundamentally, the things we can measure at any one time are the stocks. So stocks form the source for the state of the system. It's the state of the system. They form the source for inertia in a system. They kind of keep things going. And they impose delays on the system. When you have a stock, it takes a certain amount of time to build it up and a certain amount of time to drain it via deaths, say, in this case. It takes, if you have a stock of students, it takes a certain amount of time for them to graduate. They come in at a certain rate and they leave at a certain rate. If we have a stock of water in our bathtub, it takes time for that to drain out if we unplug it. Stocks tend not to jump instantaneously in this world, but sort of change over time as driven by births and deaths. Okay, now, within that video, I gave a number of examples of stocks and of flows. Can anyone Give me a few of those. Give me a stock. What's an example of a stock? Yes. Good, number of healthcare workers. I like it. Wow. Nice. Okay, number of healthcare workers. Give me another stock. How if I talk about my income? Is that a stock or a flow? Flow. It's a flow. It's actually, and I welcome both comments here. It might be a flow in. And one of the hints here, folks, is to look at how do you measure income. Suppose I were to tell you my income is $2,000.
Per month, per year?
Exactly. That's the question. And if you're asking that, if you're asking per what time unit, chances are you're talking about a flow here. We said there are 2 births in the birth rate of Saskatoon is 2. You'd ask, well, per millisecond, per minute, per day, per year. That's an indication of a flow. It's something per unit time. And that's why it's hard to measure an instant. If you freeze time, it's hard to tell how fast the Saskatchewan River is flowing outside. You froze time, you would see how much water is in a given region between two bridges, say between the Broadway Bridge and the University Bridge. You can get a sense of how much water is there, but it's hard to instantaneously get a sense of how fast that water is flowing. One's a flow, one's a stock. How about a bank account? The amount of money in a bank account, the balance. That's a stock. It builds up, and as some of us know only too well, it depletes. Does it not? Indeed. Water in the bathtub, stock, flow in, flow out to the drain, flows. The amount of sort of the knowledge in my head, you might say that's a stock of knowledge. It accumulates over time, and unfortunately it depletes, particularly if you're an absent-minded professor. So, stocks and flows. Throw out some additional ones. I asked you to think about for your examples that you came up with for causal loop diagrams. Give me some stocks. Give me some flows.
Infected patients as a stock?
Yeah, number of infected patients. Good. In principle, we may not have perfect knowledge of the world, but if we could somehow magically assess whether a given person was infected, we could go through right now, count, okay, how many of these people are infected? It might be in the record books. How about a flow? Yeah, right, people are being infected. How many people have gotten infected in the past week? People per week, people per year, people per month, what have you. Different ways of quantifying the value of a flow. How about another flow?
Amount of neutrons being produced.
Yeah, beautiful. Right. Or rate at which nuclear arms are being destroyed. Think about after the fall of the Soviet Union, the end of the Cold War. There was actually a fair bit of destruction of nuclear weapons during that period. But give me a stock that relates to that. Currently in place, the inventory of nuclear weapons, right? Speaking of inventories, so if you're Home Depot, a set of all items, or sort of the number of items in your store, is that a stock or a flow? Stock, okay. What would flows be that might relate to that? Number of things you sell, good. And or the rate, it's not so much number, it could be number per what? Per day, per year, per week, what have you. So it's a rate. It's a amount per unit time. Again, a clue to a flow. What's another flow that would affect that?
The amount you have to buy to restock.
Yeah, exactly. Things bought for restocking, right? It's going to be flows and stocks that we're building up. Okay, so any questions about sort of the basics of these concepts of stocks and flows. There are times, I've given you some broad rules. Those of you who are from physics background, or perhaps some of those from engineering background, will wonder, well, wait a minute, some of the time, couldn't we have a stock that itself is measured as change per unit time? After all, you think about position, and what's a flow into position that might, suppose I was thinking about my position along a single axis only, along this axis here. And it can decrease, it can increase, right? My sort of distance from that point. What's the flow that might affect that? Well, my velocity might bring me over, right? It's the rate at which it's increasing or rate at which it's decreasing. But you could think of, at a certain level, you could think of, well, okay, velocity 2 is a stock, and what's the flow into velocity? What's the thing that raises velocity or decreases it? The acceleration, right? So it's not always true that a stock has no per unit time. It's a general rule of thumb, and 98% of the cases that will be the case, that it's not per unit time. But there are cases where sometimes we may wish to make a quantity that's measured something per unit time itself a stock, so we can characterize its rise and fall itself. It does happen. It's just not that common. And for those of you who are puzzling about it, yes, there are exceptions like that. Yeah.
Regarding that example, could
Yeah.
you argue that velocity is
Yeah.
a flow?
It's a flow with respect to, it's a flow with respect to the stock of position. It's a stock with respect to acceleration, increasing it or decreasing it. So there it's actually serving two purposes, and actually in a system dynamics model, we would represent it with at one place a stock, and then another place it'll serve as a flow into, one place a stock, another flow into position. So, yeah.
But we would have to represent it in both ways and have a dynamic flow that is dynamically impacted by another flow.
Well, we can actually, but that flow ultimately will be impacted by stocks, and I'll come to that in just a second here. Okay. Okay. So we'll see if I can get to your question. If not, we can explore it later in the session as we're looking at some actual examples. Okay. So ladies and gentlemen, stocks and flows, these building blocks out of which we build up models. In general, what does a flow depend on? So I've mentioned flows are kind of where the action's at. That's where behavior is occurring or change is occurring to the system. The stock captures the current state of the system right now, or collectively they capture the current state, and it is being changed by flows. On what do these flows depend to determine their rate of change? Some of them just have fixed flows. You have a fixed amount of water pouring into your bathtub. Okay, but in general, the amount of water draining out of your bathtub will depend on what? Amount of water in the tub. The number of deaths occurring in people per unit time, number of deaths occurring per week, similarly, is going to depend on the population size. How do we know that it depends on it? Suppose I were to say, it doesn't depend on it at all. I can specify deaths regardless of population size. Give me a counterexample. You have no population. You have no water in the bathtub. It ain't going to drain out, right? So in general, flows depend for their values upon stocks. Now, they can actually depend on other flows, in fact, but those flows themselves then depend on stocks. There's not going to be a circular dependency among flows. So ladies and gentlemen, in a fit of mindlessness, I sort of showed the arrow that way. It'd be something like this. The number of deaths depends on the population size. We're not going to have deaths without there being some population. within our model. So we draw an arrow, sort of in a causal loop type diagram type of way, from the population to deaths, okay? Now, from a causal loop diagram standpoint, would this be a positive or negative arrow? Positive. It has positive polarity. Why is that? Because if we deaths, the rate of deaths, yeah. All those things being equal compared to the value it otherwise would have had. Good. Okay, and I would argue that there is another, from the standpoint of causal loop diagrams, there's another hidden arrow here from deaths to population size, that if we increase deaths, how does it affect population size compared to the value it otherwise would have had? It tends to go decrease it. So there's a negative feedback here. Do you see it? It goes like this. It's a negative feedback. Positive feedback here from population size to death, negative feedback back to population size through this flow. Okay, so here, ladies and gentlemen, we have a stock and flow diagram that relates to a causal loop diagram that we've seen before, or to this sort of structure that we've seen before. And indeed, mark my words, all loops within a causal loop diagram can ultimately be unpacked into stocks and flows where there has to be at least one stock involved, some state of the system that's changing to allow that loop to operate. So causal loop diagrams can be unpacked, and at least one of the items within that a given causal loop will need to be a stock. Okay, so we have these diagrams, and diagrammatically we will indicate typically that a flow, say, depends on a stock, and in general, the value of flows is either constant or depends on the current state of the system. It's going to change as the state of the system changes. On what does the value of the stock depend to change? What is it that determines the value of the stock over time?
Rate of the flow.
Rate of the flows. Flows in minus flows out. It integrates up those flows. If the flow in is greater than the flow out, what happens to the stock over time? It tends to, think about your bathtub. You've got 10 liters per minute coming in, and you've got 5 liters per minute going out. What's going to happen to the amount of water in the bathtub? It's going to increase over time, right? If the amount of water going out is greater than the the rate of water leaving, liters per minute. Can't just say liters, the amount going out. It's liters per minute. It's a flow. If that's greater than the amount coming in, then then the rate at which it's coming in, then it will be declining over time. Inflow greater than outflow, rise over time, outflow greater than inflow, decline over time. Does that make sense? Okay, let us compute. Ready to build a model? Okay, so ladies and gentlemen, I trust you have your AnyLogics ready. If you do not, I would like you to take some time to call them up right now, okay? So let's go take a look at this. So we're going to build a little model that's going to give us some experience building up system dynamics models in AnyLogic. So I would like you to close out any models you already have in place. You can do File, Close All. There you go. And now I'd like you to create a new model, File, New. Okay? And here we're going to say introductory SD. Okay? And I'm going to put in a designation here that you don't have to worry about. Okay, so introductory SD model. So we're going to have a model that, like one of the models you saw online, it's going to have a number of pieces, and you're going to first analyze them and tell me what are which are stocks and which are flows. This model is going to correspond, ladies and gentlemen, to that very first example we ran in AnyLogic, which was a model where people were divided into susceptible categories, susceptible, infectious, and recovered, okay? I will label them here. Now, for people to move between these categories, we're going to have infections occurring. These are new infections. And we're going to have people recovering. Okay? Recovering. And eventually we may have some waning of immunity, depending how far we get. Waning of immunity. Okay, so I would like you to tell me which of these is a stock. Okay, so if we put stock here, question mark, susceptible is, others? Recovered is, okay. Infectious, okay, the number of people that are infectious, good. Okay, how about infections? Okay, it's not. It's infections occurring over time. You think, how many infections were there per week, for example? This is commonly used to sort of characterize new infections, or what we call in epidemiology, we call it incident cases. It's an incident case count over some period of time. This is the incidence. Yes?
Could it also be an auxiliary variable, like total number of infections?
It could be. Very good. Yeah, that's exactly right. What's your name? Chris. Thank you, Chris. That's exactly right. It could be. We're trying to limit it here at the moment to stocks and flows, but you're absolutely right. There are some things that might be, for example, we might total these up to be non-susceptible individuals. We might have an auxiliary variable, and this would be computing, the sum of these two. And conceptually, that's a stock, but it's actually not depicted as a stock because we use a stock to depict these things, and this is simply a sum up of stocks. Conceptually, it is a stock, but here we're going to start with the basic building blocks and work up. But I like your point. And it shows thinking forward. Okay, so this is a flow. How about recovering? Flow and waning of immunity? Flow, yeah. Okay, so let's build this up. So, ladies and gentlemen, I'd like you to go to your model here, and we're going to need to add in some stocks and flows. From whence do we do that? Can you direct me? Where do I go? Okay, palette, good. And we know to go to the system dynamics area, okay? So we have a stock, we have flows, those are all we're going to use right now. We're going to have some lengths in the fullness of time. Okay, so I'd like you to drag stock in for each of those stocks there. Susceptible, and I'm going to do this a little bit quickly because you folks are quick on the computers, and I'd like to go a little bit further in some of our discussion. So I'd like you to drag one of these in for each of those stocks. Susceptible, infectious. Now we could call this infective. Naming is important in software engineering and in modeling, more specifically, okay? And then we're going to have one here called recovered, okay? You could drag these in, right? Recovered, okay. I was unartful in both the name and the positioning, so I'll be correcting that. Okay, so ladies and gentlemen, recovered. There we go. Hey, come on. There we go. Okay, Now, I'd like you to drag in flows. Now, in AnyLogic, this requires a little bit more care. Now, as it turns out, I've left just a little bit of space here, as no doubt many of you will. The key in AnyLogic is if you drop this flow in, and I'll call this infections. If you don't name it up front, you could always click on it and go to properties and click and type infections. You'll notice that initially it appears with this cloud, which means basically it's flowing out of the model. We're not interested in keeping track of where it goes. We will drag over here the stock to be on top of this flow so that it goes from into that flow, okay? So let me rehearse that again. I named this, I dragged in a flow, I named it infections, and it didn't stretch quite far enough from infectious. I could either drag this over to it, or I could drag it over to, it's not going to be very happy doing that, so I'll just drag that over to it. So then it will actually connect these. Ladies and gentlemen, there's a conservation property being ensured here. Right now, if infections occur, people move, according to the infections, from susceptible to infectious. The total number of individuals is the same. They're not flowing out of the model, okay? And then let's do the same thing for infectious to recovered, and let's call these recoveries, okay? And we can, once again, drag recovered over. Here we are. Infections, recoveries. Now, you noticed I tended to, again, naming is important. It's handy to be able to glance at a name and know quickly, or at least have a good idea of what type of variable it is. And I've named the stocks with capitals in these kind of collectively define the state of the system, and these flows with lowercase designations. They're the kind of the verbs here. Okay? Kind of like these are the proper names and these are verbs. So capital, lowercase. Okay, so that's great. Ladies and gentlemen, can we run this model now? Is that possible? What will happen if we try to run it? Yeah, there's no starting values. It's going to be an unhappy camper. So we could say save it, save early, save often. That's a good thing to do. And we could try to say run it, but it's going to be pretty unhappy. It's going to say, okay, oh, yeah, well, it's 0, 0, everything is 0. So right now it did put a default value in as 0, but really it's not going to be very meaningful right now. So we're going to have to fill in some formulae here. Okay? So we do actually have a runnable model, but it's a pretty simplistic model, to say the least. Pretty thin model. Okay. So, ladies and gentlemen, we're going to put in place some mechanisms here to add some dynamics to this model. Okay? So, I'd like to go to susceptible, and I'd like to put 1,000 people in it. 1,000 people in the susceptible stock. And now, I would like to place, in bucking the concept suggested by one of the students, I'm going to make the number of infections some value. Okay? I'm going to make it 100. Okay, now you could say 100 per what, and that points us to the fact that we need to specify the time unit. So for those who didn't do it when creating the model, you could go up to the model here, the model as a whole, and we will set this to be days. Okay? So again, going up to the model as a whole, picking days. Here is our initial value of 1,000 people, and we set the flow rate to be 10 people. What does that 10 mean? 10 people per what? Day, because we've set the time unit to be day. Okay? Great. So what do you think will happen now if we run this?
So 10 days or 100 days, everyone's going to become susceptible to infection and stay there.
Okay, great. Great. So if we were to if we were to run this thing and look at, for example, the susceptible stock, what value would it start at? 1,000. And then how is it going to change over time? Okay, linearly downward. I love it. I love it. Something like this. And what will happen then? Keep on going is right. We haven't told us to stop. We haven't told us that. We said no matter, by implication here, because infections doesn't depend on susceptible. Susceptible could be whatever value. It doesn't influence infections. There need to be actually a link here, something that shows a dependency. We don't see that. This is told, infections is told to be 10 no matter what. So it's going to go down. It's going to go into the negative regime, which is unphysical, and we're going to be fixing that. But let's go see it watch. Oh, okay. And how would the number of infectious people change here over time? What is it going to start at? At what value will it start? 0. And then whither will it go? Okay, 10 per day, and it will rise up to what value here? Okay, so at the time where this goes, what time will this be where this crosses 0? 100. Why 100? Yeah, 1,000 divided by 10. Where did the 10 come from? It's the rate of the flow. 10 people per day are coming out. There's 1,000 people to flow out total, so it's going to take 100 days. 100 days into this, the number of susceptible will be 0, and the number of infectious will be what? 1,000. There's a conservation going on here. Everyone is leaving that susceptible is going into infectious. Okay, so let's validate these intuitions, and let's go run the model. Okay, here we go. And here we see it, and we could speed it up if we want to. But if we click on this, mark my mouse, and we click this little graph here, we will see this played out in a very graphic fashion. Okay? Okay, it's counting down. The suspense is building, and there it gets into the non-physical regime. It's going negative. Okay, so we see it's drained, and the number of infectious people, if we go and we plot these, we will see a trajectory that mirrors that. It's rising, 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 etc. Okay, but something is missing here. Something that's a key element. A key, ladies and gentlemen, feedback. A feedback that I articulated earlier involving a population. Outflows need to depend on the value of that stock. It's unphysical deposit. It's just the same value no matter what happens. It needs to depend on the current state of the system. If there's no one susceptible, there's no infections that are going to be occurring by definition. Susceptible means you're subject to the risk of infection. You can be infected. If there's no one in that state, no one's going to get infected. Okay, so ladies and gentlemen, how can we fix this? How can we fix this? What? Yeah. Okay, so we're going to add a dependency here. Add a dependency between susceptible and infections. In other words, infections, the rate of infections, the number of people getting infected per unit time will depend on the current state of the system, the number of susceptibles. Does that make sense? Okay. Now, how will it depend on this? The question. Well, we're going to introduce, ladies and gentlemen, a very simple but extraordinarily powerful and common way of representing that dependency. It's the kind of the simplest way, but it also happens to be the building blocks out of which many more complicated ways are built. So we're going to take this susceptible and have infections, and we're going to insert, ladies and gentlemen, a variable that's going to be called the, and this could go by various names. A name that's commonly used is force of infection. Another name that would be used would be the incidence rate. The incidence rate. It's a chance per unit time. This is a hazard rate. It's a chance per unit time someone will get infected. So we're going to put that in there. And you'll notice that I dragged for this guy a dynamic variable in. Okay? And initially I'm just going to set it to be a value of 0.01. Okay? Force of infection. I could have called it incidence rate. I call it force of infection. What's my chance per day that I'm going to get infected? It's not a probability. It's not just a probability. It's not a probability between 0 and 1. It's a probability per unit time. And there's a subtlety there, because its value does not have to be between 0 and 1. It has to be above 0 or 0 or more, but it could be larger than 1. Turns out that if I had the value 2, it would just mean my average time until I'm infected is half a day. But we'll be coming back to that. That lies forward. Okay, so ladies and gentlemen, we put in place a dynamic variable called force of infection. And we gave it a value of 0.01. And now for infections, we are going to set this so that the rate of new infections, the number of people per day that are getting infected, will be the force of infection. And then you're going to tell me the rest. Surely what must the rest depend on? Upon what must the rest depend? Number of susceptible. It's got to depend on that. Okay, so suppose I have a 1% chance per day that I'm going to get infected. I'm a susceptible. I have a 1 in 100 chance of getting infected. That's a 0.01. 1 in 100 chance of getting infected on a given day. And now let's consider a given day. How many people on average would tend to get infected if there's susceptible number of total people at risk? So each of these susceptible people has the same chance of 1 out of 100 to get infected. Each of these 1,000 has this chance of 1 out of 100 to get infected per day. Per day. How many people will tend to get infected on a given day then? 10. Where did that come from? The number of people at risk times the chance that each of them will get infected, right? Do you see the logic of that? Each one has a certain chance, certain probability. There is this probability. So we're taking the expected value, the probability times the number at risk, right? So the rate of infections in people per unit time here, ladies and gentlemen, is force of infection times susceptible. Now let's think about that as a sanity check here. So we have 1,000 people, force of infection is 0.01, 1 out of 100 chance. Then we'll get 0.01 times 1,000, which will be 10. Yeah, that makes sense. Suppose there's no susceptible people. What will the number of infections be in people per day? 0. That makes sense. Suppose we have a ton of susceptible people, 1 million. That will tend to increase the number of infections. So it's kind of making sense about how it behaves as we vary the number of people susceptible and the force of infection. So that's good. So ladies and gentlemen, now I would like you to tell me, how will this curve change now? How many people per day will be getting infected initially? 10 people per day. So its slope will be the same up here. How quickly it's going down, right? At the start. How will this change over time, though? Will it just follow the straight line? What will happen? What will be different? Okay. So let me, I don't think this is what you mean, but let me try to use some of the words that you said. So gradual curve, do you mean something like this? Or would it be something like this? Anyone want to pause it? What's going to be happening here? Okay, so asymptotically it approached zero. So I like what I'm hearing. Man, I like that a lot. Who said that? Hey, good. Remind me your name? Connor. Yes. You were up here before. Yeah. Okay. So asymptotically it's going to be approaching zero. It's never going to. It's actually in no finite time is it going to be exactly zero unless it started at zero, right? So I like what I'm hearing. Okay, but can anyone describe to me what will this curve look like? So ladies and gentlemen, let me ask. Okay, the number of people susceptible, will that be rising or declining over time, or both? Will it be declining or rising over time? Declining. How do we know it will be declining? Okay, but broadly speaking, just looking at the connectivity of this diagram, how do we know it's going to be declining? There's no flow in, and there's a flow out. Values 0 or more, so yeah, it's got to be declining over time. As it declines, how will this number of people and how will the rate of infections, people per day, how will that be changing? As the number of susceptibles decline, how will the rate of infections, people per day, how will that be declining? It'll be decreasing, okay? So at first it will be decreasing quickly, right? And then it will be decreasing less quickly, right? Okay? And suppose now that its value has gone down from, the number of susceptibles has gone down from 1,000 to 500. How will its value be decreasing now? How many people per day will be getting infected? 5 people per day. So initially it started going down at 10 people per day. The slope of this was 10 people per day. And initially that's the case, but then it's going to start sort of tailing off. And in fact, it's going to form an exponential here. It's actually e to the minus alpha t, where alpha here is actually e to the minus 0.01 t. It's actually, and I've drawn it horribly, but it's going to look something like this. It'll tend to decrease faster at first and then slower and slower. But, you know, we're terrible about doing this in our head, and even worse, well, if you're me, in terms of drawing it. So let's not do it ourselves. I mean, these are the things computers excel at. So let's get the computer to do it. Tell us the logical consequence of this theory. What is the consequence over time? So, ladies and gentlemen, let us compute. So let's run this thing again, and we will watch as this thing changes. So I'm going and watching, and at first I don't really see much difference. It looks very similar to what we saw before. But as this changes here, ladies and gentlemen, what one will see is, and we could speed this up a bit without harm, what you'll see is a curvilinear character to it. It's actually decreasing faster and then slower. Now, similarly, if we go over to the number of new infections, you see it rising, but rising slower. When susceptible gets very, very small, when it gets to 10 people, how many people will be getting infected now per day? Or suppose it's, to simplify the calculation, suppose it's 100 people left in susceptible. How many people per day will be getting infected? 1 person per day. It will be going really slowly. Okay, now, I don't know if you're like me, but frankly, I don't care for just looking at these things truncated by sort of happenstance about when it's summarizing. So let's do better than that. Let's build up a little bit of infrastructure, okay? So, ladies and gentlemen, I'd like you to drag this down a little bit And let us go back to the palette. And let us dip our brushes into another area of the palette, to wit, the analysis area. And let us now adorn our palette with a time plot, shall we not? And here we're going to call this time plot stocks time plot. Names are important. If you want to communicate with yourself in the future, you want to communicate with others, naming things well is important. Now, I'd like you to be able to start figuring things out. So take a look at this time plot. What do you think I need to do here to get it to display what I'd like it to show? I want it to show values of each stock. What do you think I need to do? Just look at this interface. Add data items. Yeah, so we're going to add several data items, one for each stock. So let's do this quickly so we don't spend too much time on it. We'll say susceptible. And what will its value be? Its value will be susceptible. Okay? And one is just the title here. The other is actually, we could give it any name we wanted to for the title. Foo, bar, baz. But the value of it is susceptible. Okay, let's add another one. And let's call this infectious, and its value indeed with the value of the infectious stock. Boom, done. Thirdly, let us go, ladies and gentlemen, and add recovered, and we're going to say recovered. Autocomplete is your friend. What is it? Option space? Alan? Option space on Mac?
I don't know Mac that well.
What? Can you folks tell me? What is it? Autocomplete. Option space. Okay. Okay. So, ladies and gentlemen, I've added each of those items. Now, I'd like you to go down to the bottom of this, and you'll notice that there's two things that frankly are a little bit of a pain in the butt. It's in this area that's called data update, and there's a thing that says display up to 100 latest samples. I'd like you to make it 1,000 samples, and make it 1,000 time units. You'll notice that this plot, so that's in the scale, the time window here. You'll notice that this plot is set to go off first at 0 days, and it sort of is going to update itself every 1 day, and we're going to be keeping 1,000 of those. Okay? So what did I do? Let's rehearse this. I went up here, I added successive data items, susceptible, infectious, and recovered. Then I went down and I changed display up to 1,000 samples and time window of 1,000. Okay? Now, I would like you to run this thing now. Are you ready? Who needs Alan's help? Okay? Anyone need Alan's help? Okay. So let's run her. Okay? Here we go. And you should be able to see in this graph number of people susceptible, infectious, and recovered. And what lies before us, ladies and gentlemen? What do we see, and why do we see it? Why do we see this curvilinear character? Why do we see this number of people who are in that stock bending down like that? And why is this rising up to the top value in this gradual way? What's going on here? Can anyone give a narrative that explains this shape? The sound of silence. They're moving from, okay, so they're moving from one stock to the other. That's why this is declining. So that's a great start. They're like a mirror image because, yeah, they're moving from one stock to the other. There's conservation of people here. So if a person who wasn't susceptible, they just moved to infectious. So they need to total up to 1,000 between the two of them. But why is it that the number of susceptible people declines slower and slower like that? Can anyone give me a narrative to explain that?
Because the rate is dependent on the stock, and as the stock decreases, the rate decreases.
Okay, yeah. If we mean by that rate of number of people per day who are getting infected here, it depends on the stock. If there's lots and lots of people in the stock, there'll be more people per day getting infected. If there are few people in the stock, there'll be few people per day. So at first, and remember, it's the value of this flow in terms of the rate of the flow, people per day, that's dragging the value of the stock down. So at first, lots of people in the stock, lots of decline here in terms of pretty fast rate of decline in terms of number of people per day who are getting infectious. As the value of the stock goes down, the rate of flow out goes down, and therefore the stock is still being drained, but slower and slower. Right? Slower and slower she drains. Ladies and gentlemen, what we see here is a depiction of a process that we've seen before. And I'd like you to sort of document this better. I'd like you to continue to run this, ladies and gentlemen. Continue to run it, and you'll note that it's declining arbitrarily far here. But the further it declines, the slower it drains. And ladies and gentlemen, I'd like you to do something. I'd like you to perturb the system. I'd like you to disturb it. So click on susceptible and actually press pause here. You're going to press pause up here in the upper left. Okay? Click on susceptible. And then I'd like you to do something you've never done before, if I may dare you that. I'd like you to press this little edit button, and I'd like to change the number of susceptibles suddenly to 100. I have intervened as if the hand of God, I've sort of stuck in there 100 people susceptible. What do you think will happen? I've just disturbed the system. What do you think will happen? A huge discontinuity. I love it. And then what will happen? So it'll jump up to 100, the number of people in that stock. And then what will happen? It will start to decay, right? You notice that it went up, and now it's decaying in that same sort of way. And I could repeat this. I could make this, another 1,000 people in there and run it out here. And you notice it will go up. It's kind of rescaling the graph, but it will decline in the same way. It seeks, ladies and gentlemen, stasis. It seeks. It's seeking stability. It resists perturbation. You push it up, you disturb it, and it pulls back towards this value of 0. Where have we seen that before? In what sort of feedback loop? A negative feedback loop, right? It brings the system back into balance. If susceptibles rise, number of infections tends to rise, which tends to drain down susceptibles. You have this negative feedback, just like that feedback involving hunger and eating that we saw before. In this case, it's pulling the system to 0 in terms of number of susceptibles. But in a little bit, in the fullness of time, we will see that it needn't always be to 0. So, ladies and gentlemen, I would like now to go and further refine this system, okay? So, right. So, what I'd like to do now is to put in place, ladies and gentlemen, a mechanism which will put into place a similar structure for recoveries. So I'm going to phrase this in a different way to help teach you an additional principle. Okay, I'd like you to go back to the system dynamics palette, and I'd like you to drag in what's called a parameter. Okay? And I'd like to call it recovery time. Okay? Now, you could call it something else. You could call it mean time with infection. You could call it mean time to recovery. And those wouldn't be bad things to call it. It might be a little bit better. But I'll leave it at recovery time because many of you have typed it already. I'd like you to now connect that up to recoveries. And ladies and gentlemen, these recoveries, on what else must they depend logically? You ain't going to have people recovering unless there's people who are what? Infectious. So it's got to depend on infectious. Now, we're going to see another form of the same sort of loop, the same sort of balancing loop, a loop that we call here a negative feedback loop. But this structure is what's called a first order delay. So for recoveries, I'd like to use as the rate of recoveries. Well, you tell me. I'm going to let you, okay, surely it depends on infectious people. It's got to depend on that. And I want you to tell me, okay, ladies and gentlemen, suppose there's 100 people who are currently infectious. 100 people infectious. And suppose the average time it takes a person to recover is about 10 days. And suppose they have an equal chance on each successive day, equal kick of the can each of those days, each of those 10 days. So there's 100 people who are infectious, and each of them tends to recover on an average about 10 days. Equal chance of recovering any of those in sort of on a per day basis. How many people will be recovering per day, you think? Average time to recover of 10 days. 100 people in that stock. About 10 per day. That's right. Think of it this way. Suppose the average time to recover was 2 days. Well, you'd kind of expect half of them to do it one day and about half the other, right? 100 people in that stock, half of them the first day, half of them the second day. 50-50. So in short, number of infectious people divided by the recovery time. Okay? This is the second major form of what's called a first order delay. This was one form. This is another form. This first form was specified in terms of a rate, a sort of chance per unit time, probability per unit time that you'd go. This one's specified in terms of an average amount of time. And we will explore the relationship between these either later today or next time. So, ladies and gentlemen, recovery time, number of infectious, please, when it comes to your final exam, when you're staring at that piece of paper in the cold of December, and you have an average time, you divide by an average time. You multiply by a probability per unit time. This makes sense dimensionally, folks. The rates of flow are people per unit time. If we have recovery time in days, and we have people, number of people who are infectious, to get number of recoveries, people per day recovering, it's number of people divided by some amount of time. 100 people divided by 2 days. That's people per day that comes out of it. If you multiplied here, it wouldn't make sense. You'd have people days coming out of this, not people per day. That's what you need for a flow. Ladies and gentlemen, a flow always has a set of units that are the same as the units of the stock, but per unit time. So if it's flowing out of a stock, the flow is the same units of the stock, in this case, people per unit time. The stock is just people. This is people per unit time. Flow in is also people per unit time. Stocks and flows have to have comparable units, have to have compatible units. The flows units are the same as the stock per unit time. Okay. Are people ready to run this thing? You ready to run it? Let's let her rip. Oh, thank you, thank you. We're gonna put a value of 10. Okay. 10 what? What does that mean? 10 days. Because this is recovery time. Probably I should have said, if I were more careful about it, I should have said recovery interval in days, or days until mean days until recover. That would have been even nicer. I'm not going to change it now in the interest of time. Okay, so let's run this thing. Oh, well, you tell me. How do you think? No, before we run it, you tell me. How do you think this will change the dynamics now? You think it will change the dynamics of the number of people who are susceptible? Will that be different? No. No, indeed. How about the number of people that are infectious? How will that be changing? Before, what was it doing? What was it doing before? It was going up, and it took long. Oh, that's a horrible thing, man. You can see why I didn't go into art. Okay. Something like this, and continued on. One time when I was an undergraduate, my professor was drawing on the board, and then he just kept on drawing on the wall. It was with a magic marker, I think, too. It was a piece of chalk, actually. So I'm over embellishing it. In any case, so before, number of infectious people went up and kind of plateaued because there was a conservation people. How is it going to change now? Anyone? How will it be different now? Will it still be going up at first? Mark my words. I want you to think about this. Will it still be going up at first? Why will it be going up at first? I like that answer, and why? Starts at zero, good. And in order for it to go up over time, what has to be the case? Okay, for it to go up in time, under what condition will a bathtub go up over time? If the rate of inflow is greater than the rate of outflow. So infectious will be going up if the number of infections, the rate of new infections per day is greater than the rate of recoveries per day. Will that be the case initially? Why will it be the case initially? The answer, that's correct. It will be the case initially. Why is that?
There will be 0 people to recover.
Yeah, there will be 0 people to recover. There's no one here at first. So, of course, the number of new infections coming in, there's lots of people over here in susceptible. The rate of infections coming in, people per day getting infected, is much more than the number of recoveries because there ain't nobody to recover. So this will be going up fast over time. Then what will happen over time? Riddle me that. Riddle me that. Will it go up without limit? Will it go up an asymptote to 1,000? Speak on, youths. Yes?
It'll peak and then go back down.
I love it. It'll go up and then it will decline. And why will it decline? What drives its decline? Recoveries. And so for it to decline, for the number of infectious people to decline, what must be the case? What must be greater than what? Infections, yeah. The number of people per unit time recovery must be the greater number of people getting infected. Is that possible, do you think? Yeah, because at some point the number of susceptibles is going to get very low, right? And there'll be a lot more people infectious probably than are susceptible. So we'll have more people getting recovered than are getting infected. Because after all, as this is rising, as the number of people infectious is rising, the number of people susceptible is doing what? Is going down. Okay, so let's run this. Again, computers are better, but it's good to sharpen your thinking by trying to think it through ahead of time so that you can spot inconsistencies between what you thought would happen and what does happen, because that will help you refine your mental model. So we could plot this out, but now we have this nice handy graph. And so we can sit back in the luxury of our chairs and watch as the spectacle unfolds. Okay? So there we go. Peak it has already. You notice it rose, and now it's in decline. Why is it in decline? Riddle why it's in decline, ladies and gentlemen. Well, it's in decline. Number of infectious people is in decline because what is greater than what? Yeah, rate of recoveries is greater than the rate of new infections. You notice the number of susceptibles is getting very low here, so the rate of infections is smaller than the rate of recoveries. So the number of infectious people rose, plateaued, and came down. Plateaued for a minute. Now, ladies and gentlemen, why did this plateau? I mean, if we go back, and it's not visible here, but it is down here. Why did that reach this flat point? What was the case when this peaked out, when this reached its kind of point of balance where it wasn't rising and it wasn't falling? What was the case there? Why did it reach that peak?
Amounts being infected and amounts being covered
are equal. The rate at which people are getting infected is the same as the rate at which they're recovering. So it's at that point that it's in a sort of balance. It's no longer rising, it's no longer falling. Does that make sense? It's at that point it's in stasis. It's at that point that it's in this kind of equilibrium situation. Okay, so that's helpful to understand. So here we see it sort of rise, reach stasis where these two are equal, and then start to fall and start to drain. And you'll notice that its drain here, down from this point, is very similar to the drain of this guy initially. It's being drained down by this flow, a first-order delay. Okay. Ladies and gentlemen, suitable and helpful for understanding some aspects of equilibrium. Now, ladies and gentlemen, I'd like to perturb one of these things. So we're going to, again, perturb the number of susceptible people here, okay? So we're going to pause it. We're going to increase this to 1,000. Thanks, Alan, much. We're going to click here. We do this little pen, and we increased it to 1,000. And we're going to run her out. What do you think is going to happen? Pretty similar to what we've seen already, right? It's going to be kind of going down to this equilibrium where this guy maxes out at its value, number of people susceptible declines, etc. Okay, ladies and gentlemen, let's now go and stir the pot. Let us, ladies and gentlemen, allow the plot to thicken. So I'd like you to go to the palette. I'd like you, in the system dynamics area to the palette, I would like to put in a mechanism that will mirror what we did on that very first day of that example together, where we added a waning of immunity. How would we do that? From whence would that flow need to come, and whither will it go? Good. Recovered to susceptible. Good. So, ladies and gentlemen, we're going to go set that in place. We're going to go drag a flow here we call waning of immunity. Good. That's great. Now, this is going to be somewhat painful, but I will drag this down here, and I will drag this up here. Okay? Now, we can bend these things at multiple points. So if the aesthetics suit you better, you may wish to rearrange it to be something like that. Or even, if you so please, to sort of make it rectilinear in that sort of way. Logically, there is no difference between these, but in terms of aesthetics, opinions vary. Okay, So, ladies and gentlemen, I specified a waning of immunity. I would like to put in place a first-order delay where we have a mean time to waning of immunity of 270 days. How would I do that? Tell me the formulae that I should insert upon this model. So I want to have a mean time to wane immunity of 270 days. What would I do? I want to describe that with a parameter. That parameter will encode my assumption. It will encode my particular value I'm going to use for that 270 days. So I'll drag that in, and I will call it mean days, mean days until immunity wanes. How's that? We should be able to have a better name than that, but that will, given the time, that will do. Okay, mean time until immunity wanes. Okay? Okay, wanes. Okay, now you're going to tell me the formula to insert. So this is going to be a mean days until the immunity wanes, and we're going to have a first order delay, much as we did in these two, for this waning of immunity. Tell me what to insert. Riddle me that. Anyone? Okay, it's got to depend on recovered. I mean, after all, there ain't nobody to recover. No one is immunity is going to wane. Good. Okay, so it's got to depend on that. And what else will it depend on? Mean days until immunity wanes. I mean, after all, if that was just one day and we had a lot of people recovered, they'd be rushing out of there. If it were a million days, they'd be coming out at a slow pace. Right? If it was 2 days, half of them would come out in the first day, half later. So, okay, great. Roughly speaking. Okay. So we've connected this, ladies and gentlemen, up to that. We've connected it at those 2 points. Okay. So what formula should I put into this flow? Riddle me that. What formula should I put there? Speak as in a stentorian voice. Well spoken. Well spoken. And it had a ring of stentorian character. Okay. Recovered divided by mean days until immunity wanes. I like it. Okay? And these mean days until immunity wanes will be 270 days. Okay? So, what did I do? First, I connected to recovered, and I inserted this parameter and connected it to waning of immunity. For waning of immunity, the formula for that, recovered divided by mean days until immunity wanes. And I had it going from, of course, this flow from recovered to susceptible. Are we ready to go with that? Now, you tell me. How will this affect the dynamics? How do you think it will affect things? Will susceptible drain down in a monotonic way, either linearly or in this kind of curvilinear way, according to an exponent? Will it just drag down that way? Yes or no?
No.
Why not? Because now it has an inflow, okay? So it won't just drain. It will, in fact, at some point, it may start to rise. Okay, so ladies and gentlemen, let's run this thing. Let's run her. What do you think will happen? Anyone? Okay, let's run her out. Okay, so here we have this rise. You notice the number of people recovered is rising. Why are there so few people engaging in waning immunity right now?
Because it takes a long time for it to kick in.
Long time for it to kick in. So look at what's happened, folks. What's going on there? Can anyone characterize? Suppose I ran this for another hour. Suppose I truculently refuse to vacate this room for the next class and we were to just run this forward. What would happen? Yeah, it's found this equilibrium. It's found this point of balance where not just one stock, but all stocks are in this kind of balance. What does it mean for each of them to be in the balance? For each of them to have this fixed value over time, what must be the case for each and every one of them? Inflow is the same as outflow. And look, it is writ large upon the screen. 2.632, 2.632, 2.632. It's reached this kind of state of balance, the state where it's in a sort of homeostasis. So, ladies and gentlemen, let us disturb that homeostasis. Let us imagine a flight into Saskatoon filled with infectious individuals. And we will add 150 individuals who have flown into Saskatoon. Okay? They're actually not yet, the way we've captured this, they're not yet fully infectious. That will have to wait till next time. But 150 people who are ill. How do you think this will disturb things?
Infectious will jump up and that'll cause recovery, and that will jump up. Eventually will return to equilibrium.
Nice. Infectious will jump up. Recoveries will go up. This sort of flow into susceptibles will go up, and susceptibles will be rebalanced, recoveries, and then it will reach a new balance of sorts. So now it's reached a new balance. We could disturb it some more. We're going to have 1,000 susceptibles more come in, and now it's kind of rebalancing itself, but it's reached this equilibrium. Okay. Now, in the final moment here, what I'd like to do is to go add in from the palette, we're going to add in two dynamic variables, one called total population and one called prevalence of infection. The prevalence of infection will be defined. So what have I just done? I've gone to the system dynamics palette. I have dragged in to our canvas two dynamic variables, one total population and one prevalence of infection. Now, prevalence of infection will depend on the total population and the number of people who are infectious. It will just be the number of infectious people divided by the total population. Okay? So, prevalence of infection here is just going to be given by, here we go, it's just the number of infectious people divided by the total population. And you're going to tell me the total population, what does it depend on? On what does it depend? How would I compute the total population of the model? Sum of the state of the model. That's right, the state variables. Remember, these stocks keep track of the current state of the system, how many people are in each category. So if I want to compute the total population, I add up the number of people in each category. The stocks dictate the current status of the population in terms of count of people. So I add, in short, a dependency on each of these stocks in the total population. Give me the formula for it now. Susceptible plus infectious plus recovered. Okay? And now, if you run that, you will find that we have, okay, so it's complaining of being an unhappy camper about things. Infectious is used but not, oh, that's interesting. So why is it saying that I'm not using it? Infectious divided by total population. Okay, I think it's out to lunch. Prevalence of infection. It says it's used but not, okay, I think it's out to lunch. Okay, I'll just ignore that. Okay, yeah, sure, proceed here. I'm going to have to go back and see if I wired that wrong. Oh gosh, I guess it must not have connected. There it is. It's not green. Okay, there. How green is my connection? Green is the color. Okay, so ladies and gentlemen, we now have a prevalence of infection, and we could spot that, and you'll notice as we run this, the prevalence of infection will rise and then go to some equilibrium value here. It's going to reach an equilibrium value right around 0.26 here. And then if you disturb the model, you'll notice that that we could try to perturb it, and you could observe its impact on prevalence. I'm going to give you that as homework. This model that we have here with this prevalence of infection, I would like you to run this model and disturb it over time by adding people to infectious, adding people to susceptible, adding people to recovered like we did. And I would like you to investigate how does that change long-term prevalence of infection. Also, how does it change the fraction of the population that is susceptible, infectious, and recovered using a similar sort of thing to what we calculated here. This is the prevalence of infection, the fraction that are infectious. I would like you to do a similar thing for susceptible and recovered, create a graph of all three, and we'll discuss this next time. Okay? That's all for today. Thank you very much for your patience. Please do complete this homework, and I'll probably send out one other video for your perusal, and I'll see you again on Thursday. Thank you.